Okay, so let's look at a model for a fault scarp. This is a reverse fault making up somewhere in some desert somewhere. It doesn't matter where it is. Let's say there's an earthquake and this fault gets pushed up and makes a pretty sharp scarp that you can see here, just like the one in Nevada from the photo we saw before. Well, over time, this scarp is going to erode. Material is going to go from the head scarp, the top part, they call it the head wall, and be deposited on what they call the foot wall. And with this deposit, if there's things like organic material, they can actually get buried in that material that's deposited on the base of the slope. We call that material down there colluvium. Luckily, if we have something buried in there, we can eventually use that for carbon-14 dating, which can tell us how old things were alive when that event happened. Now that's great, that's one event, we could maybe get that from historical records. But if there was another event, we go back in geologic time, there could have been multiple events. This is actually, if you think about a more recent event, that one erodes and deposits on top of it, we start developing a stratigraphy. So the orangish brown on top is younger than the beige on the bottom. So we end up with what they call the principle of superposition, which says that younger stuff, all things being equal, younger stuff tends to be on top when you look at stratigraphic columns. This is one of those key concepts in geology that's really important to know. Now let's go back to the original example we showed. If we zoom in on this, you can actually see how those red lines represent faults that cut up through. Oftentimes earthquakes tend to occur on the same faults. You can see two what they call colluvial wedges, marked CW1 and CW2. Based on the principle of superposition, CW1 is probably older than CW2 unless something really funky happened. And if we can find some organic material in CW1 and in CW2, we can say, hey, there's likely earthquakes that occur at these times, find out separation between the two, and get an idea of recurrence interval. Magnitude is much, much harder in here. We'd have to do several of these trenches over a long area. And if we go 100 kilometers away and we see an area that has a colluvial wedge of the same age, then we can say, that fault must have been about 100 kilometers long, and as we said before in the last class, if the seismogenic zone or the area of brittle deformation goes down about 10 kilometers, we have 1,000 square kilometer rupture area. We can tell about how much displacement has occurred based on the plate velocity. We can make some guesses, some educated guesses about the rigidity, and come up with a moment magnitude of the earthquake that could have happened in prehistoric times. Okay, I honestly don't know that much about these piezoelectric effects that can affect animal behavior. But we do know that certain animals rely on magnetic fields for navigation, and we do know that sometimes, before and after earthquakes, these animals start acting a little wacky. Problem is, as I mentioned before, these animals could act wacky anyway, so they're not really a good solid predictor. If we could come up with one animal or even genetically modify an animal so that it really only responded to certain frequencies or certain pulses of piezoelectric or actual changes in the magnetic field that are outside the norm, perhaps it could make some rain, but we're not there yet. Here's an example of changes in the magnetic field prior to the Loma Prieta earthquake. This was a magnitude 7.1 earthquake that hit the San Francisco Bay Area in October 1989. You can see that a few days, was about 2 weeks before the earthquake occurred, there started to be these weird fluctuations in the magnetic field. And these are very small fluctuations in the field. I mean, probably 10,000 times less than the Earth's magnetic field over. But you could filter it out, and that's what these guys did. And you can start seeing these funky little anomalies. It got a little crazy, then it started dying off, and then all of a sudden, pow, it really spiked when the Earth quake occurred, and it was still a little funky for a while afterwards. Now, the theory behind this is sort of the same thing that guards makes your watch work. Quartz watches. Some minerals have properties that they emit certain consistent frequencies of electricity. If there's an Earth has magnetic fields, there's constantly magnetic field, rocks are constantly exposed to magnetic field. So if you start to deform those rocks, you change the shape of the crystal matrix of those rocks, you can actually start causing these weird fluctuations in the magnetic field. So the assumption is that before an earthquake, the rocks are really stressed and they start kind of cracking and creaking a little bit and twisting, and all of a sudden, right before they break, they're actually putting out these kind of very subtle changes in the Earth's magnetic field. Again, it hasn't been consistent. There's been massive earthquakes where there's been no change in the magnetic field, and there's been changes in the magnetic field when there haven't been these earthquakes. So it's not very consistent yet, but some people think there's promise there. One thing that I saw, which I thought was a bit of what they call snake oil back in the States, something that says it's going to cure one thing but not do another. I saw an advertisement in Port-au-Prince, Haiti, for earthquake early warning systems using P waves. Sophisticated enough language, I said, oh, maybe there's something there. So I looked into it a little bit more. The idea is because primary waves travel faster than shear waves and faster than surface waves, if you can detect the P waves early enough, you can actually send off an alarm, then use the speed of light to communicate that to emergency facilities. Now, this could come really in handy in major urban areas. If you think about if you had an automated system that was triggered by a certain P wave magnitude that could be 100 kilometers away, for instance, then you could have an automatic trigger to shut down gas lines or critical infrastructure. And then the next few seconds behind, when the shear wave comes in, it could really be a few seconds, maybe 10 seconds later, you can actually have these things shut down. So you close all your gas lines off, so when the shear waves happen, the surface waves happen, it will actually shear the pipes. You won't have gas leaking in your neighborhood. So this is an interesting way of reducing the risk, reducing the vulnerability of certain systems using real science. We're not going to do probabilistic seismic hazard assessment in this class. This is the way most of the real earthquake prediction happens in the real world. You have the system of looking at a variety of sources, earthquake sources that could affect a site. Maybe there's only one fault, maybe there's multiple faults you have to take into consideration. You look at how frequently earthquakes of a given magnitude occur during this time or recur during this time. You have a good record like shown here. You can hammer that down. You can also do some modeling of ground acceleration. Maybe you have seismometers that are recording the acceleration of the ground during earthquakes. Maybe you use a computer model that says if you have a certain rock strength and apply a certain force or a certain energy level to it, energy frequency to it, it's going to respond in a certain way. Then you put all this together and you say, okay, we're going to look at probability in this certain area, a certain distance from a fault with a certain recurrence interval is going to have an acceleration that exceeds certain threshold. So it might be that, okay, they give out language that every 200 years you have a 90% chance that this particular area is going to have an acceleration that exceeds 1g, 1g being 1 times the amount of acceleration due to gravity, which is 9.8 meters per second squared. So if that's a vertical acceleration, in this case, you're momentarily weightless because there's enough acceleration to actually throw you up into the ground. That's how hard 1g is. This is the language that's used in the field. And what they do, which is actually kind of genius, is make these very clean maps that do a very good job of visually showing you where the hazard is. You can see a lot of red along the San Andreas fault zone, and right along the fault itself, you see those bright, almost whites. And that's where, obviously, the most hazard is. That's where the highest probability that a certain acceleration is going to be exceeded within a certain time frame. What this does is provides really helpful information to insurance agencies because they can actually quantify the risk, saying, oh, there's a 98% chance that there's going to be a 1g acceleration in San Francisco in the next 30 years. They can use that sort of information to design buildings and save money. So if I'm a contractor and I know that there can be there's this percentage of a certain acceleration being exceeded, I can I can design to do that. If it's going to be more early that's going to happen, it's going to happen within 10 years, I'm going to put more extra money into that building, whereas I might skimp a little bit if it's going to happen within the next 30 years, which would be the lifetime of the building. We're looking at risk, and what earthquake prediction does is it reduces uncertainty. We're understanding the hazard here, which is the earthquake, and we're going to get into vulnerability, but we're really not going to go into that. I'm going to have that section saved for the social science class and the economics. So we keep looking at how can we reduce uncertainty, not by looking at vulnerability so much, but looking at vulnerability in terms of the hazard and really trying to hammer down that hazard. Thanks very much, and we'll look forward to seeing you in class next time.